Here's my first example. We have some chocolates and I'm going to choose 3 of the chocolates. What I'm interested in is how many different combinations of 3 chocolates could I take. This is in contrast with permutations, where the order does matter. With a combination, the order doesn't matter. How many 3-letter words can we make? And remember that words don't have to be real words. Looking at the number of permutations, I could have A, B, C, B, A, C. Or I could use a different set of 3 letters, C, D, E, etc. But the number of combinations, A, B and C would be considered the same as B, A, C, because I'm using the same 3 letters. So I could have A, B, C, or I could have A, B, D, but I couldn't then have D, A, B because I've used that combination of letters. If you've looked at permutations before, then you may have come across this formula that the number of permutations, when you're choosing from n objects and you want the number of permutations of R of those n objects, then it's n factorial over n take R factorial. In this case, we were choosing from 5 letters and we wanted the number of permutations of 3-letter words is 5 factorial over 2 factorial. So that just leaves us with 5 times 4 times 3, 60. So 60 permutations of 3-letter words chosen from the 5 letters. And here they are. You may have written them all out if you didn't know this formula. Now let's consider the number of combinations of 3 letters chosen from the original 5. Looking at my 60 3-letter permutations, you can see that I've actually grouped them. So this group here contains all the different permutations containing the letters A, B and C. Now that would be considered as one combination of the 3 letters. So that would be my first combination, A, B, C. I've got another group of 6 that contains all the permutations of the letters A, B, D, and again that would be one combination of those 3 letters. Altogether I've got 10 groups of 6, so 10 combinations of 3 letters chosen from the original 5. Remember, I started with 60 permutations of 3 letters, but I've got them arranged in groups of 6. So if I divide by the 6, that leaves me with the 10 combinations of letters. Now using my formula, I've divided by 6. Now where does the 6 come from? If I want to make a 3-letter word from the letters A, B and C, I would have 3 options for the first letter, then I've used a letter, so 2 options, 1 option, or 3 factorial permutations of each set of 3 letters. So really I'm taking my original formula for the number of permutations and dividing by R factorial. And I can simplify that formula to n factorial over n minus R factorial times R factorial. That's 5 factorial over 2 factorial times 3 factorial. 120 divided by 2 factorial is 2, 3 factorial is 6, so this is 120 divided by 12, 10. Generalising some of these ideas. If we just want to arrange n objects, it's n factorial. If we just want to arrange some of the n objects, so R objects chosen from n, we take the n factorial and divide by n minus R factorial. But remember that each combination of R objects itself has R factorial permutations. So if I just want the number of combinations of R objects, I need to divide by R factorial, which simplifies to n factorial over n minus R factorial, R factorial. Now this is abbreviated to NCR, or it's often just said as N choose R. It's also abbreviated to NR. Now there is an equivalent NCR for permutations, which is NPR, but this version, NR in brackets, always means N choose R. There's no equivalent for this notation when we're talking about permutations. In the first example, I want to know how many combinations there are of 3 objects chosen from the 8. This is 8 choose 3. Or using the formula 8 factorial over 5 factorial times 3 factorial. That's 8 times 7 times 6 divided by 3 factorial, 56 combinations. In the second example, I'm choosing 2 objects from the set of 5 letters. So this is 5 choose 2, 10 combinations. In this next example, we're arranging 5 people in a line, but we're given that the 5 people are selected from an original group of 8. So the word arranged here gives us a clue that we're actually looking for the number of permutations of the 5 people. There's a couple of different ways that we can approach this. Firstly is to just consider it as a permutations problem. So 8p5, and we know that the formula for that is 8 factorial over 8 take 5 is 3 factorial. I know that 8 times 7 is 56, and 6 times 5 is 30, times 4 is 120. I'm just going to leave that there for a moment. There's another way I could approach this problem, which is to say that I will first choose the 5 people, and then I'll work out how many different ways I could arrange the 5 people. So if I do 8 choose 5, that's 8 factorial over 3 factorial times 5 factorial. Looks very similar to this, 8 factorial over 5 factorial times 3 factorial. So I'm left with 8 times 7, or 56. That's the number of groups of 5 people I could choose. But I then need to arrange the 5 people. So that will be 56 times 5 factorial, which I know is 56 times 120. So either method, going straight to permutations, or first choosing and then arranging, will result in the same answer. It's worth making a note of this connection between the number of permutations and the number of combinations. If I want the number of permutations, I first choose the R objects and then I arrange the R objects. Before I work through these next 3 examples, I'd like you to pause the video and try them on your own. In example number 4, we're asked to find how many combinations of 3 pieces of fruit can we choose from a selection of 8. That's 8 choose 3. It's actually the same as question 1. If you remember, we already worked out 8 choose 3 and it's 56. The only difference here is that we now have a context. Up to now we've been working out these answers manually, but it's also important that you know how to do them on a calculator. 8 choose 3 is 8 factorial over 5 factorial times 3 factorial. So try putting this into your calculator and making sure that you do get the answer of 56. Now, most calculators actually have an NCR option. NCR, and normally you would then enter the N and the R separated by a comma. So try locating this button on your calculator, putting in the numbers and checking that you do still get the answer of 56. In example number 5, we have 20 people on a committee. We want to make a subgroup of 4 people, so that's 20, choose 4, or you should be able to locate the NCR button on your calculator to work this out. In example number 6, we're not just choosing 6 people in total, but we want to specify that we do actually want 3 males and 3 females. So in total we've got 8 males and 9 females. So to select the 3 males, I need to do 8, choose 3. And to select the 3 females, I need to do 9, choose 3. Now what do I do with these two numbers? Well, I've got my groups of males here, and there are however many you found of those. I've got my groups of females, etc. And I need to be able to combine each group of males with any possible group of females. So for every group of males I would have a certain number of groups of females, and I could combine any of them together. So mathematically what I'm doing is multiplying the 8 choose 3 by the 9 choose 3. Again, I would suggest that you pause the video and try this question for yourself before watching my solution. Example 7. A normal pack of 52 cards, shuffled and 7 cards dealt to form a hand. How many different hands are there? Well, we just need to choose 7 cards from the 52. How many of these contain the ace of hearts? I want the ace of hearts, so if I separate out the ace of hearts, I've got 1 ace of hearts chosen from itself. But the other 6 cards need to be chosen from the remainder of the pack. How many contain exactly 3 of the 4 kings? From the 4 kings, I need to choose 3 of them. And now I've got 4 more cards to choose for my hand to make it up to 7. I need to choose them from the remaining 48 cards. Now in the final part of this example, I want it to include at least 1 ace. So if I say, well, it includes 1 ace, that means I'm choosing 1 of the 4 aces, and my remaining 6 cards come from the remaining 48 cards in the pack. Number of combinations that contain 2 aces, I've got to choose the remaining 5 cards in my hand from the 48 that are left. 3 aces, and finally it could contain all 4 aces. Now this will give you the right answer, but it's quite long-winded, and so one tip when you see the phrase at least 1 is to consider, well, what if it contained no aces? So from the 4 aces, I would choose none of them. Now that's the number of combinations that contain no aces. I already worked out how many different hands there are altogether, so I just need to subtract the answer I just found from the answer to part A. And you should check that on your calculator just to make sure